Can everyone hear me? Okay, great. Hello, everybody. This talk was a quick overview of the presentation. I'll start the motivation for transient searches. Some of the previous work's done in the field. Either. You may have had a project where it's going on, and so when it was being built, and you can see that it's well, you've got 12 individual CCDs. Yes. And so, as you've heard, no doubt, the XMM level data, we're reaching about 15,000 observations now, 3.2% sky coverage with 984,000 detections. We've got a total of 8.8 years of PN exposure. And then when you add in MOS1 and MOS2, that goes up to 30 years. So it's actually longer than the amount of time that it's been up in space. I mean, technically. 4,207 Earth orbits. On average, you get 65 plus or minus 45 detections per observation. So it really depends on where you're looking. And the one we all love, 27 billion photons. And so that's 3.3 photons for every person on the planet. Key point, the XMM pipeline only searches for variability in sources that have more than 100 total photons in the source. And this only corresponds to about a third of the detections. So there's a lot of stuff that doesn't really get scanned for variability in the which are now thought to be magnetars, of which there are about 30 known at the moment. X-ray bursts, type 1, which are caused by thermonuclear runaway explosions on neutron star. Type 2, which are a lot rarer. I'm not entirely sure what the process is there, something to do with the disk. Supernova, X-ray flashes, and supernova X-ray breakouts are thought to be at the very beginning of supernova, and we get loads of X-rays coming out. X-ray binaries, the classical variety, the timescales vary on huge ranges. Their counterparts, ultraluminous X-ray sources as well. We know there are now neutron stars in these sources, which often exceed the Eddington luminosity by several hundred times. Very interesting. TDEs and QPEs, tidal disruption events and quasi-periodic eruptions, two events that might be closely related, are also possibly detectable within an XMM observation. And then down here, we've got dwarf novae, cataclysmic variables, and also stellar flares, which everybody loves, of course. Okay, so some previous publications in the field when it comes to looking for transient and XMM Newton data. So in 2020, we had Pastor Marzella, and this was the first iteration of the EXOD paper. And they were successful in finding 4 extragalactic type 1 X-ray bursters. And so we are continuing this project. And well, we'll get to that. And then at the same time as that paper came out, we had Alpha Tau, and they were looking for supernova shock breakouts in the XMM archive. And they limited their soft energies, and they were looking in 5 different timescales, 100 to 100,000, 10,000 seconds with log binning. More recently, we've had extras. So yeah, they used a method of Bayesian blocks and fixed bins, 3 energy bands. They searched for pulsations. They included the bad time intervals, which we'll go into a little bit. And they successfully identified 136 new transients, ranging from 900 to 5,000 seconds in duration. Very recently, we've had Andre Ruiz with his statics pipeline for the detection of X-ray transients in 3 dimensions. And this is a very sophisticated state-of-the-art algorithm that uses Bayesian blocks in pacing and denoising using wavelets. And I'm sure he'll tell you much more about that soon. Okay, so how has EXOD got to the point where it is now? So back in 2017, we had the first iteration, which was called Variability Electron, which is a bit of a mouthful. We then had Inez, who came over and upgraded the algorithm, included the GTIs and BTIs, separated all of that stuff out. And then back in 2019, we had the first run on the archive. But however, this only included data up to December 2017. So that's been almost 6 years now. So there's a lot of stuff that we haven't really looked at since. And then more recently, we had Maitreyi, who was also working on this project. And she added in MOS1, MOS2, and she also ran it on the whole pipeline. And now most recently, Erwan and I came over to this project. And well, the code was in such a kind of a rough state because so many different people had been working on it over the years. And it was almost as if one person would write a bit of code and then the next person didn't want to touch that part. So they just added things on. And so it was quite difficult to work with. So we've actually fully rewritten the algorithm. And we're working currently as we speak on the detection algorithm. And so we've reached very much, the performance increases have been substantial as a result of that. But the key thing is we've got some modifications to the detection algorithm. And unfortunately, because that's such in-work type stuff, we're literally doing it as we speak. I won't be covering a lot of the details that we're working on at the moment. Okay, but how does it work? So we start with events list from XMM Newton. Here it's from 0.5 to 12 keV. And we take a time column, X and a Y column, and then we bin our counts in 3 dimensions, essentially. What you end up with is a data cube. So this is of size Y, X, and time. And each cell in the data cube, essentially we can specify to be Y arc seconds, X arc seconds, and T seconds in the time dimension. So what does the data cube look like? So here are 2 data cubes. The first one is binned at 750 seconds, and the second one is binned at 50 seconds. And so there's a lot to discuss here, actually. So if you look carefully in this side, there's a few sources. There's one here, one here, one here, and one here. There are a few transient sources. There's one right there, so naturally there's a lot of transients in here. When you lower the time binning down, however, you notice that, well, first of all, there's just a lot less photons in every frame. And so that makes things a little bit tricky to detect variability. You also notice that, well, the amount of cells that we've got in our cube increases substantially from 677,000 to 10.2 million at 50 seconds. And well, it's still okay in the memory domain. It's not taking a huge amount of space in the computer. Okay, so one of the things that I mentioned a little bit earlier was these good and bad time intervals. So if you can just click play on this video, I'll quickly explain where these are coming from. So essentially, these are caused by soft protons from the sun. So here's an observation from the SOHO Observatory from 2003 by NASA. And you can see this big old flare goes off, and then the whole detector was covered in all of these soft proton flares. So it's essentially analogous to this, except in XMM. And what ends up happening is when you have these bad time intervals is that it covers the entire field of view of the detector like this. And everything that you were able to see, well, now it's just smothered out. Here's a particularly bad observation that we've got where we had to basically almost throw away like 90% of the observation, and we only keep the bits in white here. So it's a big shame to just throw away that much data, and that has been the approach up until this point in a lot of analyses. So we are working on trying to figure out a way in that space. Okay. Click in there. Yeah, click again. Oh, okay. I think we're good. Yeah, okay, sorry about that. Okay, so anyway, so I mentioned the data cubes. Here they are. Obviously, this is just each frame of the data cube playing as a video. So we take our data cube and then we calculate what is extremely vaguely called here a variability image. So ask me more about that at the end, I guess. And then, so here I've plotted the variability image in 3D, and in theory, the peaks in our variability images should be where we have the most variable regions. We then threshold this image by putting just anything above this level and anything below this level. We just separate into 2. So we end up with a binary image like this. And then we use scikit-image to very quickly calculate centroids on each of the regions that were detected. So there's 2 points here. There's the normal centroid, which is just the center of this particular 2-pixel joint connection here. And then there's also this weighted centroid where we've weighted it by the strength of each pixel. And so we use this weighted centroid to convert back into RA and DEC for source positions. And so currently we're roughly about 9 arc seconds of inaccuracy. So I think there's probably some slight work to do with exactly where we're putting the grid and that kind of thing. And then additionally, we can very quickly extract the light curve. And we've rewritten everything from scratch. And so it was previously taking a few thousand seconds to run each observation. Now we can do it in about 4. So we can very quickly iterate on it and see what needs to be changed. Okay, so now we've got regions and we've got our light curves. We will then do some cross matching, first and foremost with the XMM catalog. Then we'll go and cross match it with Sinbad. And then we'll potentially do Gaia and loads of others. Yep. Okay, sorry. Yeah, as you know, as we've heard this morning, cross-matching is actually far more complicated than a single arrow pointing from this to this, but we will take the care to do it properly and read the manual. Next up, we take the light curves, and we're going to get a lot of these as well. So we need to do some post-processing. So we'll likely conduct a whole bunch of different variability tests, which are established in the literature. The Gregory-Laredo test, for example, is using Chandra data, and it's done on the raw event time of arrivals. We could also calculate false alarm probabilities by comparing to a Poisson simulation, just Monte Carlo it and see how many times we get what we get. And then additionally, we can work on a sort of filtering algorithm to just make our lives easier, because we don't want to look at 200,000 individual light curves. So we can just extract features from each of the light curves that we get out and then do a quick classification, and then we can just look through the classifications, which saves us a lot of time. Okay, so current status. So we fixed a load of bugs with the centroiding. There were some issues with the good time and bad time intervals. We vectorized all the calculations, which led to significant performance improvements. We're now using pre-existing libraries like SciPy and scikit-image to do a lot of the calculations, which again speeds things up dramatically. One of the slight differences, which is really just a detail, is that we're using the sky coordinates x rather than the CCD coordinates det x, which doesn't really change much, really. We've messed about with the variability formula, but we're still messing about with the variability formula, so that's why I haven't put the variability formula here. Yeah, we've increased the speed of the source detection method, and this is working really well, and we still have all of this stuff to do. So all in work. And of course, as I mentioned, we wanted to point out one of the interesting sources that got pulled out. So we haven't run XOD since, well, 2017 officially. And so we ran it on maybe the 5,000 most recent XMM observations, and this source popped out at us, and we were like, this is interesting. So you've got the observation. It's basically flat for the entire time. And then right at the end, you've got a huge peak, and then it kind of mucks around here and then comes down. Well, actually, the observation just ended. So there's a bit of a shame that it was right there at the end. So it's a burst lasting maybe 1,000 seconds. And the key thing is it's actually an extremely hard spectrum with, so these are the 3 light curves in 3 different bands, soft, medium, and hard. There's basically nothing in the soft. There's not much in the medium, but most of it's coming in the hard part of the spectrum. We checked for optical counterparts and we didn't see anything. We still need to check for radio counterparts, as Olivier mentioned to me the other day, and yeah, we're still doing that. Yeah, and it's roughly 10 to the 36 ergs per second, assuming a distance of 8 kiloparsecs roughly to the galactic center. And we're not saying it's a magnetar, but it's potentially consistent with a magnetar spectrum in quiescence, and then also the burst being extremely hard is also possibly consistent with the magnetar. So here's a plot of the spectrum. So you can see it kind of peaks around, I don't know, that's like 7 or so. And yeah, so maybe it's a magnetar, maybe not. So we'd love to hear your opinions on that. It's still very early doors on this particular source, so bear with me. Okay, so future work, we want to to do simulations to test how well a source detection algorithm works. We basically need to do end-to-end simulations. We put in a source, we vary its flux, we see if we can detect it, we see if we can't. And yeah, that's great. Another idea we have is actually to merge MOS1, MOS2, and PN, which Andrea mentioned earlier. And this is to increase the signal to noise. And also, it just gives us more sort of, I can't think of the word right now. Okay. Some spectral information may be useful additionally. So currently, we don't use any spectral information there. Again, using the flaring bad time intervals. And yeah, the key one here is potentially applicability to Athena data. So this will come when we do the simulations for XMM. We'll also do the simulations for Athena data and see how well it performs for that. Okay, and yeah, thank you everybody for listening, and I'll take any questions.
Thanks, Norman. Time for questions, but let's swap the order this time. First question, are there online? Okay, then back to the room.
Yes, thank you very much. This is Felix First from ISAC. Thank you very much for the very good talk. I didn't quite understand. So you're saying you're calculating the variability map, and then on that map, you're trying to find your sources, like you're doing the R index on the sources.
So I deliberately did leave that a little bit vague, but yeah, I'm listening.
No, but I was just wondering why don't you do it just in the count image, like directly, instead of going to variability image first?
Yeah, I mean, that's one of probably the best way to do it actually would be to take each frame in your cube and then run one of these source detection algorithms, which we know work extremely well. And the only reason we don't do that is a question of speed. We want this thing to run fast, and then we'll look at the second stage to see if the source is real or not, essentially. It's just too time consuming, especially when you're going down to the small bins that we're planning to go down, like 5 seconds, 1 second, which is a lot further down than they've done in extras. It's just going to cost way too much to run the source detection on every single frame for every single observation in the XMM archive.
Okay, yeah, that makes sense. Thank you.
Yeah, very nice work. Just a comment. For statics, we prepare a large set of simulations, and they are public. They are already online, so you can use it if you need.
I think we'll take you up on that, because why reinvent the wheel again? Thank you.
And for the following questions, may you mention your name for those online who can't see you?
Hi, Stephen Chen. Quick question, and maybe a bit basic. Why does it look like in the light or data cube that the I guess the background photons are going from top to bottom?
As in, there's more photons at the top?
Or like, it seems like to me the background photons.
Oh, I think that's when you're seeing patterns where there aren't any. I don't actually think that there's anything to do. It's pretty much uniform across the field here. The only thing that you might be seeing is actually the flaring bad time intervals. When you see that, so let me go back a bit, because it's a bit easier to see in the other image. Okay, this thing is not working with me. Come on. Okay, next slide. Here we go. Yeah, so whenever the whole frame gets brighter, that's usually when you've got the soft proton flares going over your entire detector. Yeah, okay. But I don't think there's anything different above, like from the top compared to the bottom. Are you saying that you're thinking that like the photons are moving down? Yeah, I think it's just a visual effect. It's mostly just Poisson noise, really. Yeah.
Hi, I'm here. There's a very good question. I know. Just a very quick thing. So in your, because you said you use a kind of a two-step method, like you go to the variability image and then you see if there is something, and then you go and double check using the usual standard method that I understand. How many false detections do you get actually? Are you really saving time by doing this in 2 steps?
So we haven't done the simulations to actually give you a number on that.
Roughly understand.
The idea is essentially we will cross-match it with the XMM catalog and get rid of anything that has already been detected and checked for variability. And then we've got essentially missed through the sieve. Yeah, it's going to be some time-consuming work at the end on the post-processing side, but it's just part of the process, I think.
I'm not Axel, Didier speaking. I mean, it looks very much like, I mean, trying to dig out some very small signal in images. I mean, have you looked at the machine learning techniques to spot those little excesses in this image? Because there are huge application using this, and it could be very fast. The related question is, can you reduce your data to improve the speed without losing information?
Yeah, I mean, with machine learning being all the rage at the moment, it is potentially a very good application for some of these algorithms that are out there. We haven't actually looked at any directly, but if you have any suggestions and things that we might be able to do, then we would more than happy to hear those.
We'll talk to you.
Okay.
Thanks.
Anything online, meanwhile? Then let's thank Norman again.
Thank you.